Okay, we're talking about 6.1, angles and their measure. All right, so you should learn how to describe angles, to use degrees and radians to convert back and forth, and also to solve real-life problems, which are often going to involve degrees, minutes, and seconds, to break angles up into smaller increments, as you'll see. Okay, angle comes from the Greek language. The word trigonometry means measures of triangles, so obviously we're still talking about the measures of triangles. That's where all this trig comes from. As we talked about before, trig comes from similar triangles here, where the ratio of, say, this side to this side is always the same. Opposite to adjacent is tangent, and it's always 1/2 in this case. So the angle is determined by rotating a ray around its endpoint. So we're going to start with the initial side. We're going to rotate that and get to what's called the terminal side, to use some vocab. The vertex of the angle is going to be here. The angle in standard position is going to start on the positive x-axis and rotate counterclockwise. We are going to rotate positive for counterclockwise and negative for counterclockwise. And in doing so, we can get different angles that are the same, actually. I could rotate positive by this positive amount alpha to get to this location, or I could rotate by this negative amount beta in order to get to the same exact location. Different angles, but same direction. Same thing here. I could rotate positive alpha, or I could go all the way around again to get back to the same location to beta here. Different angles, but same direction. Okay, obviously 1 degree is going to be equivalent to 1/60th of a rotation. So that's down here, just 1 degree. There's going to be times that we're going to want to break that up into smaller increments, which we'll find that we can break up 1 degree into 60 parts and call those minutes. And we can take 1 minute and break that up into 60 parts and call that seconds. So we'll go over this in the homework, but that's where our degrees, minutes, seconds come from for latitude and longitude. They're based off angles at the center of the Earth. And what you find is that a 1 degree angle at the center of the Earth right here equates to about 70 miles. And that's too big, obviously. If we're going to talk about angles, using angles to describe latitude, for example, we need smaller increments, and that's where that's where minutes and seconds come in. So we will use that in some of our application problems. You do want to know the quadrants, so obviously the first quadrant between 0 and 90 is the first, and then you have the second, third, and fourth, so don't forget those. Let's do a quick example of finding a coterminal angle. So if we have the positive angle 390, that's the angle that we get when we go all the way around 360, but plus another 30. So that angle is right here. Now we want to subtract 360 from that, and we get all the way back to 30 if we do that. So it turns out that 30 degrees is a coterminal angle. It's in the same direction, but it's just 360 degrees less than our original angle. We could do the same thing with positive angle 135, which is over here. We can subtract 360, in which case we're going to bring it back all the way around to the same spot, but it's going to be a different angle. In this case, it's going to be negative 225 if we take 135 minus 360. That's the angle that you get when you rotate this way, right to there. Same location, same direction, but different angle. Okay, don't forget about complementary and supplementary angles as well. Complementary angles add up to 90, supplementary add up to 180. Now, radian measures something you might not be as familiar with because usually we use degrees. But radian is just what we get. Basically, 1 radian is what we get when the radius is equal to the arc length, as you'll see here. So if this distance here is equal to this distance, that's what we call 1 radian. And it comes right from this relationship, which I'm going to give you next, S equals R theta. This has always got to be in radians for this formula. So I'll describe. And so if you want to know what 1 radian is, S equals R times 1, divide both sides by R, and you'll see that's when these are equal, that's when you get 1. So when S equals R, you get 1. So basically that means the same thing we had up here, is that when the arc length S is equal to the radius R, that's what 1 radian is. Okay, you'll find out then that 2 radians would be somewhere up here, and then 3 radians would be over here, and this is obviously 3.141592 radians because it's in this direction here. So there's our pi, and then obviously if you go all the way around we get 2 pi again. So radians is something you might not be as familiar with, but we are going to use it a lot in this class. In fact, anytime you see a decimal, like if I give you an angle of 7.2 and you don't see the degrees symbol here, what that means is 7.2 radians, which is going to be all the way around. Here's 6.28, 2 pi, so it's going to be all the way somewhere in the first quadrant again. So here's the definition of radian that I already gave you. It's the measure of central angle that intercepts the arc that has equal length to the radius of the circle. So 1 radian's here, 2 is here, 3 is here, 4 is somewhere down here, 5's here, 6 is here, and you just keep going around and around the circle. All right, you're going to have to do some example problems of finding, like, complementary angles. If I want to find the complement of pi over 12, what that means is pi over 12 plus some angle theta has to be complementary, so it has to add to 90. All I have to do then is subtract pi over 12 from both sides and get a common denominator by multiplying the top of this one by 6. And when you subtract, you get 5 pi over 12, which is my answer here. The supplement for 5 pi over 6, same thing. 5 pi over 6 plus some angle theta has to equal to 180, which is just pi. So I can subtract 5 pi over 6 from both sides and make sure I get a common denominator and multiply top and bottom by 6. That gives me 4 pi over 6 for my angle, which simplifies to 2 pi over 3. And then another example, finding a coterminal angle with 17 pi over 6. Just add or subtract 2 pi in this case, because that's one full turn, right? Just add or subtract that from this original value, and that will give you a coterminal angle. Now I need a common denominator, so I'm going to multiply the top and bottom by 6. When I add these, I get 29 pi over 6, which I can't simplify, so there you go. So because 360 equals 2 pi, then obviously pi equals 180. That's what we're going to use to convert back and forth between angles and degrees. So converting from degrees to radians, we're going to multiply this. To convert from radians to degrees, we're going to multiply by this. So here's an example then. If I have 135 degrees, multiply by pi radians over 180 degrees so that the degrees cancel. And then when you simplify, you just get 3 pi over 4. Same thing here. Going from degrees, multiply by pi over 180, degrees cancel, you get radians, and turns out that 180 goes into 540 exactly 3 times. You just end up with 3 pi. Okay, we're going to do some applications with arc length. So here's the relationship for arc length between arc length, radius, and theta. Keep in mind that theta has to be in radians for this formula to work. So that's going to be very, very important for this formula that theta is in radians. But it will give us a relationship between arc length on a circle, radius of that circle, and the central angle. So this is what you're looking at right here. There's the arc length we're talking about, there's the radius, and there's the angle. Linear speed, we won't talk a ton about this, but obviously we would just take the arc length divided by time, because rate is equal to distance divided by time, or speed is equal to distance over time. Well, in this case, the distance is our arc length. So that's where we get S over T for linear speed. We won't use angular speed much at all, but that's just the central angle divided by time. So instead of talking about distance over time, we can talk about angle over time, and that would be obviously angular speed. Some applications then, we're going to find area of a sector. I like to do it by taking small angle theta divided by the total angle equals the area of the sector divided by the total area, which the total area of a circle is pi r squared. That's the way I like to do it with a proportion. Small angle to big angle equals small area to large area. The book does use a different, though, they use this formula. You're more than welcome to use that formula. I did put it on your formula sheet. That will do just as well. You just plug in the radius and the central angle. Okay, so here's an example then. Let's say we have a sprinkler at a golf course that has a radius of 70 feet and goes through an angle of 120. Find that angle. I like to do 120 divided by 360 equals the area I'm looking for, which I call x, over the total area pi r squared. So I just solve this right here. 120 goes into this 3 times, so it's 1/3. You can multiply both sides by this pi times 70 squared, and that gives you your answer. If you do that with pi, we could do 4,900 over 3 pi, or as a decimal, we could do 5,131.3 approximately. And the units on that, since our radius was in feet, are going to be square feet.